In this video, we'll start talking about DC current circuits. And when you think about a circuit, I want you to think about the voltage starting at the highest point, the positive end of the battery. So you can imagine if you're running a race and you come charging out of the gate or from the starting line with as much voltage as possible. But if it's a long race, you're going to get tired. So similarly, the voltage is going to drop as it hits light bulbs and other sources of resistance. Now, once it comes back to the battery, we say it's at 0 voltage. So then the battery will increase the voltage again. If you've ever played with Hot Wheels or Matchbox toys, and sometimes they have like little rollers, and you put batteries in and they zoom, they shoot the car across the track. Well, the car goes through the track and then comes back to basically the battery where the little rollers are and gains more energy. It's like it's gaining more voltage and it can zoom around again. The current doesn't drop, only voltage drops. So whatever the current is here is also the current over there. There has to be current in the other wire. It has to complete the circuit. You might say, well, there's a gap there. That's just the battery itself. That's not indicating an actual gap. There's chemical reactions occurring in between here, in between the positive and the negative plate to keep it going. But let's say it's a 1.5 volt battery. Well, the voltage here, right before it goes into the light bulb, is 1.5 volts. But we say then it's 0 volts, and then it's 0 volts all the way back. But there's still a current running through. You could still get shocked if you touch the wire over here. It's still current. So here we've got a 1.5 volt battery and a 15 ohm light bulb. This symbol here is the symbol for resistance, the zigzag. That resistance could be inside a light bulb. So a traditional light bulb has a tungsten wire in there, and that's the resistance. A lot of light bulbs we're moving now to fluorescence and LEDs especially. They still have some resistance. They just work on some different principles, but they do still lose energy, but not as much as a traditional light bulb, the Edison light bulb. Well, getting the current is easy. V equals IR. IR. So I is V over R. Using Ohm's law, there's a 1.5 volt battery, 15 ohm light bulb. So I think we can guess that that's going to be 0.1. Double check on the magic number machine. Yeah, it's 0.1 amps. Or 100 milliamps. Often electricians and electronics people will use milliamps because it's just easier. Now the voltage drop across the light bulb, it's the full 1.5 volts. So it says, well, graph the path. Graph the voltage versus what's going on. So the voltage starts out at 0. Then inside the battery, it pumps it up to 1.5 volts. 1.5, we'll put that on the graph. Then it goes through the top wire. So it's at 1.5 volts while it's going through the top wire. And then here, this line that's coming down, this is the bulb. The bulb reduces that voltage back to 0. So now it's 0, and it has to go back to the battery to get zipped up again. The current doesn't change. The current is 0.1 amps here and 0.1 amps here. The voltage at the top wire is 1.5 volts, 0 volts. Current can still flow with the 0 volts. It has to complete the circuit. So you can see here's the same picture here. And then after going on the bottom wire, it'll go back to the battery and get revolted again. Just like capacitors, with resistors or light bulbs, or there's resistance on other parts of the circuit too. That's why computers get hot and cell phones get hot, things like that. We could put them in series or parallel. We're going to spend a lot of time dealing with series and parallel here. It's important to know that the same current passes through all the resistors. If you have a string of Christmas lights, or a string of lights like in a tent, or like at a circus or a festival or something, an outside thing, the bulbs are all the same brightness. You don't notice and look at the lights and say, oh, as you go down the strand of lights there, they get dimmer and dimmer. They don't. They all have the same current. All bulbs are just as equally bright. We do lose voltage each time, though. So each bulb, the voltage will be a little less, and we'll deal with that in a little bit, either a few minutes or in the next video. For resistors, resistors behave in the opposite fashion as capacitors. For resistors in series, you simply add them up. So if we had 3 light bulbs, 1, 2, and 3, just 3 light bulbs here in our string, we could say, well, if we add up all their resistances, that would be the same as having one big resistor or one big bulb taking all the voltage there, because they're in series. So for example, this one has a resistance of 100 ohms. There's one light bulb, and that's a common way to represent a light bulb in a circuit diagram. In fact, I drew these online on an online circuit diagram. But here we've got 2 light bulbs. So just as you'd expect, you simply add them. You could have 100 ohm light bulb, or 2 100 ohm light bulbs, or 1 200 ohm light bulb if they made such a thing. Then here, same deal, you just add them, but we put another bulb in the process. So that would be the same as if we had a 300 ohm light bulb. Exactly like capacitors, we can split them. In this case, it's also, there's something's the same, but not the current. The current will split. Think about it like water. Water's not a perfect analogy, but it'll do here. If I had 90 gallons per minute, and I had the channels split, like it was coming out of, I don't know, a dam or something, and then there were 3 ways we could send it. We're sending it to 3 different towns. Well, maybe only 30 gallons per minute could go this way, and only 30 gallons per minute could go that way, and only 30 gallons per minute could go the other way. So for resistors in parallel, the current splits, but the voltage is the same. So if this is a 12-volt battery, it's 12 volts here, 12 volts here, 12 volts here, 0 volts, 0 volts, and 0 volts over there. There's a 12-volt drop. Now, to get the equivalent resistance, we need the reciprocal formula. R1 plus R2 plus 1 over R3 plus as many as we need. Now, you might only need 2 if you have 2 bulbs. You might need 3, 4 if you have 4. But this is the opposite way the formula goes. For capacitors, you would simply add them. For resistors in parallel, 1 over the resistance equivalent is equal to you add up all the reciprocals, and then we don't forget to take the reciprocal at the very end. And we'll do some math on that in the next video.